We'll encounter a measurement problem when trying to express the size of an AC quantity. How do you grant a single measurement to the magnitude of something that's constantly changing? In this diagram, we've arbitrarily labeled the vertical axis in units such that the amplitude of Vmax is 1. So we've just said that the max voltage here is 1 unit. Therefore, the negative Vmax is also 1 unit. It's just an arbitrary decision so that we can make things fit on a graph. Therefore, since Vmax is 1, if we square the voltage, as we did in the average value, we get 1 again. So here what we see is we've got this dark line, Vmax here, V of t, right here. Its value is 1. So what does squaring that result in? Well, at 0, we're going to, 0 squared is just 0. Right. 1 squared is 1. Negative 1 squared is 1. Again, 1 squared is just 1 right there. Well, what happens in between? At a half, at a half Vmax, 0.5 by 0.5 just comes down to 0.25. Here we would do 0.5 times 0.5 is 0.25. Minus 0.5 times minus 0.5 is again about 0.25, or is exactly 0.25, right? And so we see that although the squared function reaches the same maximum, it's got a little bit steeper slope on either side, right? So V squared of t is going to be all positive, and it's no longer a sine wave, right? The squared value is no longer a sine wave. It's a little bit steeper. It kind of looks like a sine wave, but it isn't actually one. So those are kind of the two plots that we have there. What we would like to do is have some method of averaging this periodic voltage and currents that offer a good representation of how much current or voltage is actually being supplied. A meaningful measure, something that allows us to compare between periodic AC waveforms of different shapes and DC voltages and currents. And put this way, the answer almost becomes obvious. What we really are interested in is we would like to compare different waveforms based on their ability to do useful work when applied to a load resistance. I.e., really what we want to know is, can we compare the amount of power delivered to a load between different waveforms? If you recall that the power in a resistive circuit is given by the product of voltage and current, or P equals IV, which when manipulated to reflect power delivered to a resistive load can be written as P equals V squared divided by R, or P equals I squared R. So we've got the power is equal to I squared R, or power equals V squared over R, right? Those are just saying the same thing. In both of these formulas, we can see that the power is proportional to the square of the voltage or current applied to a resistance. And this is the essence of the most common measurement for AC waveform amplitudes, the root mean squared, or RMS value. The RMS value provides a measurement that tells us the equivalent value of current or voltage in an AC system that delivers the same power as a DC voltage. The RMS value is derived by first taking the square of the entire function, then taking the average value or mean of that function, and then undoing the squaring by taking a square root. So the RMS stands for the root of the mean of the squared function, or RMS, root mean squared. Squaring the curve is done to eliminate the negative signs, as the square of the negative numbers becomes positive. So what we end up with is, I'll write it down here, Vmax, or V peak, times the cosine of omega t plus phi, so we want to square this whole function, right? So we would put that there. And you get Vmax squared and write that as Vm squared cosine squared of omega t plus phi, which is what we were showing previously, right? We've got the maximum voltage squared, which in this case was just 1 times 1, and then the steeper function is a cosine squared function. When we take the mean of the squared waveform, we then take the mean of the squared waveform. To find the mean value of a function over the period, you just integrate over one period and divide by the length of that period. So to solve that, we would do 1 over t, or we're dividing by the length of the period. We integrate from some time t, doesn't matter when, to one period later, which is t0 plus t. You know, often that would be from 0 to t of v max squared cosine squared omega t plus v. And then we're integrating over time, so dt. So that's actually how you find the average value of the squared waveform. You integrate over the waveform. That gives you the total area bound by the curve. You want to do it over one period. And then you divide by the total length of one period. So that's average value. Although this equation looks complicated, the result of this mathematical formula is relatively straightforward. It's just Vmax squared over 2. So not too bad if you were to actually carry that calculus out. The next step is to undo the squaring that we did in step 1 by just taking the square root. So if we take the square root of Vmax squared divided by 2, well, the square root of Vmax is just, the square root of Vmax squared is just Vmax, or Vpeak. And then the square root of 2 is, unfortunately, an irrational number, so we get just the square root of 2. So we get Vmax over the square root of 2. Another way to write this is 1 over the square root of 2 times Vmax. Or 0.707 times Vmax, approximately equals 0.707 V peak, right? Where I'm using the terms max and peak interchangeably. Thus, the RMS value of a sine wave is just really easily calculated. You don't even have to use calculus, as 0.707 of the peak amplitude. In summary, the RMS voltage or current gives us a method of translating the varying values of alternating voltage or current into equivalent constant value that tells us whenever the magnitude of a DC voltage source would produce the same amount of heat energy dissipated through an equal resistance. In the circuit shown here, we have the same load resistance, 2 ohms, 2 ohms. They're both dissipating the same amount of power in the form of heat, 50 watts and 50 watts. Because the AC voltage source is equivalent in terms of power delivered to a load to the 10 volt DC battery, we would call this a 10 volt AC source. More specifically, we would denote its voltage value as being 10 volts AC RMS. Sometimes the alternative terms equivalent or DC equivalent are used instead of RMS, but are meant to signify the same quantity. So you might say I have 10 volts DC equivalent, or 10 volts equivalent, or something like that. But in this class, we'll say 10 volts RMS. RMS amplitude measurement is the preferred method to relate AC quantities to DC quantities or other AC quantities of differing wave shapes when dealing with measurements of electric power. For other considerations, peak or peak measurements may be the best to employ. For example, when determining the proper size of wire, known as the ampacity of the wire, its ability to carry current, to conduct electric power from a source to a load, when determining the ampacity of a cable, we use RMS current measurements. It's the best to use because the principal concern with current is overheating of the wire, which is a function of power dissipation caused by current through the resistance of the wire. And since it's a power dissipation issue, we use RMS. However, when rating insulators for service in high voltage applications, peak voltage measurements are the most appropriate, because the principal concern here is insulator flashover caused by brief spikes of voltage, which is irrespective of time and particularly related to the peak value of the voltage. Simple conversions also exist for other pure waveforms. I'm not going to show the derivations of those, but for a sinusoidal waveform, remember that RMS is 0.707 times the peak value. The average value of the waveform, if we were to do the squaring only, is 0.637 times the peak, and the peak-to-peak value is 2 times the peak. For a square wave, the RMS value and the peak value are the same thing. The average value and the peak value are the same thing. The peak-to-peak value is just twice the peak. Finally, for the last kind of most common periodic waveform, the triangle wave, the RMS value turns out to be 0.577 times the peak. The average value is 0.5 times the peak, and the peak-to-peak value is 2 times the peak. And just remember that these average values are being calculated on squares. Well, what if we have non-pure waveforms? So these conversions really only exist for pure waveforms. The RMS and average values of distorted wave shapes are not related by the same ratios. So here we have some sort of distorted wave shape. It makes no sense to determine the RMS or the average value of those. Really the only thing that we can determine is what the peak-to-peak value is. And in this case, we actually have to measure the maximum peak value and the minimum peak value and determine the distance between the two. We can't just use the doubling of the peak. So let's work an example of determining the RMS of a current wave. So we've got a sinusoidal current having a maximum amplitude of 20 amps. The current passes through 1 complete cycle in a millisecond. The magnitude of the current at time equals 0 was measured to be 10 amps. And we need to find the frequency of the waveform, find the angular frequency of the waveform. We want to write the time domain expression for the current waveform, and then we want to find the RMS value. And it's relatively straightforward to calculate angular frequency if given frequency. Remember that omega is equal to 2 pi f, right? So we had a 1 complete millicycle in 1 second. So what that means is f is cycles per second. If we do cycles per second, that's 1 cycle in 1 millisecond. You do that math, you get a kilohertz. Therefore, the angular frequency is just 2 pi times a kilohertz, or 2,000 pi. Radians per second. To write the time domain expression for current, we must make note that we were told the maximum, meaning the peak value, and we calculated omega to be 2,000 pi. We can then substitute these values into the standard time domain expression for current. So we had I of t, so current as a function of time, is equal to the peak value, cosine of omega t plus phi. To be specific, we'll give it a subscript I. Remember, this is measured in amps. You may notice here that I used a lowercase value. Typically, lowercase values are used to represent AC quantities, while uppercase values are used to represent DC quantities. So we can rewrite this as I of t equals, well, we were given the peak value as 20. We calculated already the angular frequency omega as 2,000 pi. So now this becomes 2,000 pi t. What about the phase shift? Unfortunately, we don't know the phase shift yet, so we'll have to stop there for right now. Right. So what we'll do to figure out that phase shift is use the information regarding the instantaneous value of the waveform that we are given to determine the phase shift. So what we were told was that at t equals 0, the instantaneous value of the waveform was 10 amps. So clear my slide. I'll rewrite that. I of t equals 20 cosine of 2,000 pi t plus the phase shift. That was in amps. What the information that says at t equals 0, the instantaneous value was was 10 amps. How we write that is I of 0, because remember the argument I of t goes here, so we put in equals 10, right? We were told it was 10 amps. That's the instantaneous value. The time domain expression is still 20 cosine of 2000 pi. Now we need to plug in 0 for t plus v sub I amps, right? So what's going to happen here? We get 10 amps over 20 amps equals cosine of 2000 pi times 0 plus phi. That just simplifies to cosine of phi sub I. Right? So cosine of, or arc cosine, excuse me, of 10 divided by 20, which is 0.5, is equal to phi sub I. So pull out your handy dandy TI-89s and you will find out that this is equal to 60 degrees. So taking all that information, we can now write the time domain expression I of t is equal to 20 times the cosine of 2000 pi, which is the angular frequency, times time, plus the phase shift, which is 60 degrees. And that's a current waveform, so that's in amps. So this is what we would call the time domain expression for the current waveform. If we evaluate it at a time t, that's what gives us the instantaneous value. So what about the RMS value? The RMS value is a pretty straightforward calculation. We'll say the I RMS, it's just, remember, it's 0.707 times the peak value, or the peak value divided by radical 2. In this case, peak value was 20 amps. We divide that by radical 2. What does that give us? 14.14 amps, or so I RMS, the RMS current. If you've been paying close attention, you may notice something kind of funny about the way that I've been writing these instantaneous expressions for current. If you look, I've got 20 cosine 2000 pi t plus 60 degrees. What's funny about that? 2000 pi is in radians per second. I multiply that by t in seconds. That gives me 2000 pi radians. I wrote 60 degrees for the phase shift here. Shouldn't I have written it in radians? Yeah, I should have. I should have written that in radians, and then they would have added together, and the whole thing would have represented an angular quantity. For some weird reason in electrical engineering, phase shift is almost always written in degrees, and frequency is almost always written in radians per second, which causes kind of a contention inside the argument of the cosine function. You'll find in signal processing and in other fields, they'll go ahead and put this in radians, but not in the power system. Power system engineers tend to leave that in degrees, and you have to do the calculation to convert from 60 over. So that's pretty easily done. Just remember that there are 360 degrees in 2 pi radians. They're equivalent, right? In the unit circle, there's 360 degrees in 2 pi radians. And so therefore, if we were to do the math, there's a 60 degrees equivalency. So we just multiply 60 by 2 pi radians divided by 30, and we would have converted that over to 1.05 radians. Right. And again, 60 times 2 pi radians per 360 degrees, 1.05. But for some reason, phase shift is almost always written in degrees instead, so you'll just have to do that calculation.